Okay, everyone, let's get started. My plan today is to go over quiz 5 and then finish up the system Verilog content, and then I will do another quick demo for showing you how to set up the IP block in Platform Designer. So quiz 5 was due, this is the one that was due last night. It says the first question, there were 5 questions. First one says, consider the Verilog module shown below. Should say system Verilog module, but basically it's a module with an always block in it, but the question says how many input signals are specified, so all you have to look at there is the module line, and we've got 1, 2, 3, 4, right? So that one's should be pretty easy. Next question, consider the system Verilog module seek. Assume the module is reset with a reset pulse at the start of execution. What is the value of the state in the first 3 clock cycles after the reset pulse? So this is kind of tricky because this is implementing a state machine, essentially. The way that I would recommend doing it is just building a table, and we know that when you reset, the state gets reset to 1, 0, 0. So that's our first cycle, and then you calculate the next state based on the current state. And so I've got it split out. I've got the next state split into 3 separate bits. So the next state for 2 is going to be a 0. In fact, it's always 0, so that whole column is going to be zeros. The next state bit 1 is going to be the previous state bit 2. So this guy is going to be a 1. Next state 1 is going to be 1 because that was the value of state bit 2 in the current cycle. And then the next state bit 0 is going to be the current state 1 OR with current state 0. So the low order 2 bits will be ORed together, and the answer there will be 0. Everyone see that? Okay, so then on the clock edge, this value will then be carried down to be the next value of state. So 0, 1, 0 will then be the current state in cycle 1. Does that make sense? So next state 2 is 0 because it's just hard-coded 0. The next state 1 is going to be the previous state 2, and remember 2 is the most significant bit, so that's 0 here, so that will make that 0, and then the next state 0 will be a bitwise OR of the lower 2 bits of the current state, which is 1 OR 0 is 1. Does that make sense? And then that 0, 0, 1 is then carried down as the current state, and then next state 2 is 0, next state 1 is going to be 0, it's going to be the first bit from the current state, and the next state 0 is going to be a 1 because it's 0 or 1 is 1. Make sense? Now we don't actually need that 0, 0, 1. This last 0, 0, 1, we never actually use it because that would be what's in this column in the next cycle, which we don't care about. So I didn't even need to calculate the next state for the third row. Everyone with me? Any questions? So it says 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, give the value of signal A for the first 3 cycles. Similar question. So I just built a similar kind of table. We start out with A. A is a 3-bit signal. It starts out as 1, 0, 1. And then now in this case, oh, by the way, so this question, I realized after the fact that I didn't tell you in lecture the difference between these 2 different equal signs. So I ended up setting all the answers to correct. So all of you should have gotten credit for this because I didn't actually cover this. It was my fault. But the way this works is this equal sign is called a blocking assignment. And this equal sign, which is actually a less than equal sign, meant to look like an arrow, is a non-blocking assignment. And the difference is that when you have a blocking assignment any subsequent statements in the always block will see the updated value of that assignment. Okay, so in other words, when you assign A in this line and then you use A as an input in the next line, right? The next line will see the updated value of A. That is as opposed to a non-blocking assignment, which is the less than equal, that doesn't take effect until the whole always has been evaluated, the whole always block. Which means that if I had used a non-blocking statement in the first line of code inside this if statement, then the second line of code would have been looking at the old value of A, not the new value of A. Does that make sense? So what would that mean? It would basically mean that the first line wouldn't have any effect at all. If these were both the less than equal assignments, then that first line of code wouldn't have any effect. Actually wouldn't do anything. But because I used a blocking here, then the value of this A is carried forward to subsequent lines within that always block. Does that make sense? And it's kind of confusing. But normally in sequential logic, you're supposed to use, by convention, you're generally going to use these non-blocking assignments. And the idea with those is that they don't take effect until after the whole always has been evaluated, right? Which means that if you assign the same signal twice or more than once, only the last one takes effect, right? Which is still the case here, except the difference is that because this first line had a blocking assignment statement, it just means that any data dependencies inside that always block are honored as they were if you were writing in Java or C, right? Otherwise, you don't have these internal data dependencies if you just use the non-blocking assignments. Does that make sense? It's kind of can be confusing, and generally you don't do this. I just had this question when I was to explain the difference between the two. But generally you won't have this type of, unless you have unless you're trying to build a kind of a complex expression and you want to break it into multiple lines, which is what's happening here. See, in this case, I'm taking A and shifting it by one bit to the left, and then I'm doing an XOR with 1, 1, 1, which just flips all the bits. So this does a left shift by 1, flip all the bits. Because when you XOR by 1, it just flips the bit. Right? Okay. Okay, so what's happening, in order to calculate this then, I built this table and I have this row called intermediate, which is the result from the first line of code, right? So if A is 101, which it is when you reset, then when you shift by 1 bit to the left, you get 0, 1, 0, because that leading 1 gets shifted off, and you shift in a 0, so it's 0, 1, 0, and then that's what you get after the first line, and then after the second line, you flip all 3 bits, you complement all 3 bits, so you go from 0, 1, 0 to 1, 0, 1. Okay? And so that 1, 0, 1 is then carried down into the next, as the next value. And so that 1, 0, 1 gets shifted and complemented, and as it turns out, nothing ever changes, it just stays as 1, 0, 1. So the answer to this question is 1, 0, 1, 1, 0, 1, 1, 0, 1. But like I said, no matter how you answer that question, you will have gotten credit for that. Okay, any questions? Okay, what's the problem with the following code? So this one has always underscore comb, and there's no sensitivity list there, meaning that this is intended to implement combinational logic, meaning that it's supposed to just be a type of assign statement, essentially. And so in this case, you have this problem, though, because it's written as if it were sequential logic, right? It's written as a counter, where it's counting A, but you can't build a counter with combinational logic. So you would need clocked logic for that. Otherwise, you end up with a combinatorial loop, right? Meaning that, you know, you're going to have A equals A plus 1, but that addition is going to happen as fast as the adder can add, and then it's going to go and add again and again and again. It will never stabilize, right? It'll just be running as fast as the logic will permit, right? Make sense? So what you want in here is an always underscore FF, or just an always with at pause edge clock, which will make this count once per cycle, which is what we're going to use in this next lab. We need a counter in there. Any questions about that? Okay, so the always statement there should be combinational, but it has a cycle. Yeah, there's a cycle. There's a cycle in the sense that the input depends on the output. Okay, and this is the last question, I believe. Yeah, what are the first three values of A generated from the snippet below? This is another one of these kind of clocked logic. In this case, A is a 5-bit signal. It resets at 10101. Now in this case, I broke it into individual bits. So the current state is 10101. The next state uses this concatenation operator where it takes the new A is formed out of a bit twiddling operation in which it takes the least significant bit of A and then combines that with two copies of the bit 1. So basically 0 and then, I'm sorry, 1, A bit 0, and then 2 copies of A bit 1, so 0, 0. So I grouped that into, one column. So it's 1, 0, 0. And then next we have not A bit 3, which A bit 3 is 0, so that would be a 1. And then A bit 2 XORed with A bit 4. So you just look at these two guys. 1 XOR 1 is 0, and so we have a 0 there. And so this value 10010 will then be carried down into the next cycle. So that's 10010, and then you just do the same thing again. So A bit 0 is 0. A bit 1 is 1, so we copy that twice, 1, 1. A bit 1 is, A bit 3 is 0, so that becomes complemented, that's now a 1. And then A bit 2 XOR A bit 4, which is 1 XOR 0 is 1. And so that gives us 0, 1, 1, 1, 1. So now we're copy that over here to the next state, 0, 1, 1, 1, 1. And then actually at that point we're done. There's no point in, we don't really care about what's coming next because we only care about the first 3 cycles. So that's the answer, 0, 1, 0, 1, 0, which is the reset value. And then from there we go to 1, 1, 0, 0, 1 and 0, 1, 1, 1, 1. Make sense? Okay. So if you understand those questions, then that's the extent of the system Verilog that we're covering in the course. Just basic, some simple always statements and some combinational logic. And so with that, you can build hardware. Okay, now if we switch back here to lecture 3. Okay, a couple other simple things that shouldn't be a big deal. You probably already gathered this stuff, but we haven't talked too much about this always com, but I mentioned that an always statement can be used for sequential logic or complex combinational logic. And again, sequential is clocked, combinational is not clocked. So if we build this always underscore com, which is also the same as saying always at star, if you see that notation, it just means that if any of the signals that are treated as inputs inside the always block change, it activates the always statement. And so always com, and this thing is implementing a mux. So it says out 1 equals bar. If select equals 1, then out 1 equals foo. So this ends up creating a mux where the inputs are foo, actually bar and foo, and if select is 0, it's going to forward bar, and if select is 1, it's going to forward foo, right? Now this could have been written, you could have done this as an assign block with a ternary operator, which is how I would have written this. But in this case, it's an always, and because we're using an always com, that gives you access to using an if statement. All right, so we're using an if statement here as opposed to a ternary operator. The effect is the same, though, by the way. They're going to be synthesized the same way. So what's different about this? Well, I don't have an else here. I just say if select equals 1, then out equals foo. The problem is that if you do this, and let's say that was the only line of code you had, you don't have anything for this always to assign to out 1 if select is 0. So normally if you do that, how does the synthesizer treat that? Like the synthesizer, what is it going to set out 1 to if you get through the always, and because of the path you took through the if statements, you don't ever assign the output, or one of the outputs, any of the outputs. Does that make sense? You guys with me? So like the if statements, may not ever assign out 1. That'll end up creating a latch that'll get synthesized as a latch, meaning that if you don't assign out 1, the synthesizer will assume that you want to retain the previous value of out 1, which implies now that there's memory in this thing. You have to end up creating a latch in there, right? And so normally if you did that with just an always at star, it would just be happy to create a latch. Right? Now again, I'm assuming that this first line isn't in there, right? I'm assuming it's just the if statement, right? So if you had done that, it would create a latch, and actually it'll give you an error in this case because it says always comb. So in this case, the way this always is written, you're telling the compiler this is supposed to be combinational logic, and if it has a latch in it, it's not combinational, it's sequential, it means it has memory. And so it would actually give you an error. But if this is just a generic always at star, then it would just create a latch, and you might not intend for that. So the way to fix that would be to put an else on here, or you can do a default statement. You can do a default output, which is what I'm doing here. So this first line of code sets out 1 to bar, which is the default output, and then the if potentially changes that if select equals 1. Now you might say, well, wait a minute, I mean the muxes don't change the output. Once you set a select, it should switch to the input that you specify. But as I was mentioning earlier, if you assign an output twice inside an always, only the last one matters, right? The previous ones are ignored. So in other words, I set out 1 twice, but because they both are assigned in one always evaluation, only the second one matters. So this is treated, so this effectively becomes an if, then else, right? Does that make sense? Okay, now notice I use blocking assignments here, which is the convention for an always that does combinational logic. Now you might say, wait a second, what about your data dependencies then? If you have blocking, didn't you say that there's, yeah, but there's no data dependency, so it makes no difference here. You could have used equals or less than equals here. That makes no difference in this always because out 1 is only used as an output. I never use it as an input, right? Now if I had used out 1 as an input in here, then it would matter whether I use blocking or non-blocking assignments, okay? The reason I use blocking is just because it's the convention. I don't know why that came to be, but conventionally you're supposed to use equals for always that are combinational logic. You don't have to though. It's not enforced by the compiler. But there can be behavioral implications though if you use outputs as inputs, right? Okay. There is also a case statement. Oh, sorry, this is not the case statement. This is this is just setting multiple outputs. Yeah, so here's an always statement that sets multiple outputs. I mean, as you would imagine, that's fine. I mean, but just keep in mind that this always block is going to get synthesized into a glob of logic, and it's going to be driving all 5 of these guys with push-pull drivers. So you just have to keep in mind that this always statement owns in terms of outputting Y1 through Y5, right? so you don't want to you have to be careful not to double drive any of those. Okay, question?
Aren't there more output variables? Oh, wait, I see.
No, the module has just Y1 through Y5.
It's making each of them 4 bits.
Yes. Yeah, so that's, this 3 down to 0 gets inherited to those guys. That's a shorthand. So in other words, because I didn't list a type for Y2, it's assumed that the type is output logic 3 down to 0, which was the most recent type that was given in that list. But that's the same way that it's kind of like, in Java, if you type int a comma b, they're both integers. Although in Java, you can't do this kind of thing on method arguments, though. Like when you have your arguments on a method, you have to give the type for every argument. Although this isn't a method, this is a module. This is a port, pins or input-output ports for a module. So it's not like a method, right? But it's kind of similar. But anyway, point is that yeah, this is a shorthand. But to be honest with you, most professionals would not write it this way. They wouldn't use the shorthand. They would have output logic Y1, and then on the next line, tabbed, aligned, output logic Y2. Usually you you don't necessarily want to write code like this. This is not a great style because it's not as readable as if you had, fully defined each one of the inputs and outputs. So I'm not recommending that. Okay, yeah, so that's really the only point of this example is that you can have multiple outputs for an always. Okay, now here's another thing is you can use as a case statement, which is a switch statement, basically. And so you're probably, you will be comfortable with this. It's similar to a switch statement in Java or in C. It works pretty much the same way, except you don't need a break. So you have case data. So this is a 7-segment decoder. Data is the inputs, 4 bits. Segments is 7 bits. That's the output. And so we have case data. Data is the input here. And then we have these cases for each of the 4-bit values. And for each of those, we assign segments, right, which is the 7-segment value. You don't need a break after each of these cases, but if you have multiple statements, you need a begin and end for each of these. Make sense? But in this case, there's no begin and end because there's no begin and end for example, the input case of 0, 0, 0, 0, because there's only one statement there. And then you should have a default statement, much like you should in any language. And then there's case and end case. You end that with end case. Personally, I never use case statements. I use those nested ternary blocks, but that's up to you. That's a stylistic thing. There's also this, I don't have the case Z. Okay, there's variations on case where you can put don't cares in here. There's one called case Z. For whatever reason, I deleted that slide, but if you're interested, you could look it up. But the difference is with case Z, you can put some of the bits on these cases can be don't cares, which could be marked as question marks, but otherwise it's the same. All right. Oh, there it is. Sorry, I do still have the slide. Yeah, case Z. Yeah. So in this case, if the input is 1, don't care, don't care, don't care, which means that if it's any value from 1, 0, 0, 0 to 1, 1, 1, 1, then I'm going to do this one. Otherwise, if it's 0, 1, 0, 0 to 0, 1, 1, 1, I'll do this one, right? So yeah, that's the case Z. Okay, and then blocking versus non-blocking, this is what I just described. Less than equals a non-blocking assignment, equals a blocking assignment. These only apply to always blocks. These only apply to assignments you make within an always block. So here's two different modules, each with an always underscore FF. Both of them have 2 assignments. Both of them have the second assignment depend on the first assignment. So this says N1 gets D, Q gets N1. So these are both identical. The only difference is this one uses non-blocking assignment, this one uses blocking assignment. And as I mentioned, if in this case, the second line sees N1 here, right? But it sees the old value of N1, not the value of N1 that has been, oh, sorry, scratch that. This one does see the new value of N1 because these are blocking. So this N1, so D is set into N1, and then Q gets N1, which is effectively D, right? So what ends up happening is this creates a flip-flop that basically just has D as the input and Q as the output, right? Which would have been the same if you just had substituted D on this second line and deleted the first line, right? So these two lines are redundant. Okay? The first line is redundant. Now over here we use the non-blocking assignment, and in this case D, N1 captures D and Q captures N1, but Q is capturing the old value of N1 from the previous cycle. And D gets, and Q gets, so Q gets the old N1 and N1 gets the current D. So what this ends up doing is creating a shift register, because it creates two flip-flops where the second flip-flop is getting the output value from the first flip-flop, which had been set in the previous cycle. So I don't know if you guys might not have done this I wish they still did circuits like this in 211. So if you take flip-flops and you connect them in series, it creates a shift register, and every cycle the bits just work their way down. Work their way down the flip-flops. And so that's what this will end up creating. You can create a shift register this way in just one always statement by doing this kind of thing. In fact, in this case, it doesn't even matter what order these lines of code are in. You can swap them, and it would make no difference. In this case, it would make a difference. If you swap these, then I think it would. No, maybe not. I don't know. I've never tried that, actually. This gets kind of complicated with this blocking stuff. I have to try that. I actually don't know that for sure. But in this case, I know for sure if you switch the order here, it won't make a difference. Because again, assigning to N1, this is basically saying I'm putting D into N1 and N1 into Q, but this N1 is the N1 from last cycle. Okay, any questions about that? Okay. Okay, now one thing I want to mention here too, one last thing, and I mentioned this, I talked about this in lab, but we used to teach Verilog in this class, and we switched to System Verilog when the 611 textbook went to System Verilog. System Verilog is basically, I don't think they're still updating Verilog. I think they've the newer versions of Verilog are System Verilog, right? So there has been this this push to go into System Verilog. System Verilog is like, you could think of it as like a C++, and Verilog is C. System Verilog is a superset of Verilog, but there are some exceptions. There are a few exceptions to that, and the one I want to call out here are the types. So in System Verilog, we use type logic for everything. All the signals are logic. The only exception to that for us is going to be a gen_var for the generate statement, which I'll talk about here in just a minute. But all the signals are of type logic. And then if you have a multi-bit signal, you can have logic with multiple bits. But generally a logic is like a one bit signal. Logic has 4 different values though, in simulation at least. There's 0, 1, and there's X, which is conflict, and there's Z, which is high impedance. I didn't cover that in this class though, because we're not doing simulation. We're just going to put everything on the board and test everything on the board. So in the case of the hardware, it's just 0 or 1. So it's meant to be a binary signal. But in Verilog, the logic type is actually split into 2 types, wire and reg. It's the same thing. Both represent a binary value. The difference is that wire is A wire is a structural net expression, or a net, structural net value, meaning that you use wire for any bit that's driven by a structure, which is like another module that you've instanced, or by an assign statement. Whereas reg is only used for signals that are driven by an always block. Now you might say, what in the world is the difference? I mean, I thought you said that an assign block and an always block are basically just translated into a circuit, right? A digital logic circuit. So what is the difference? I don't know. I don't know why they did it that way. It's obnoxious, and that's why they fixed that in System Verilog. In System Verilog, they got rid of that distinction. The way this will affect you is that if you're writing Verilog and you type something as wire when it should be a reg, you'll get a compiler error, but you'll know exactly what it is because it's pretty clear what it is, and you just go back in your code and change it. It's not a big deal. I mean, it's something that is easily fixable, but it's something that you constantly have to deal with in Verilog. Now, why did I bring this up if we're using System Verilog? Because in Platform Designer, when you create an IP block, that IP block has to be written in Verilog. I don't know why. It's a limitation of the tools, but it's not a big deal because this is the only difference, for the purpose of what we're doing in class. So it's not a big deal, but you should be aware of that. Okay. 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 Another thing is parameters. Parameters are a way that you can customize a module when you instance it. So for example, let's say you have a module that's a RAM. You're going to want to be able to say, you're going to want a generic RAM that you can then customize its depth and width, right? How many entries it is, and how many bits you can read or write in one cycle, right? If you have even a flip-flop, like if you have a flip-flop you want to instance as a module, which I'm not sure why you'd want to do that, but in that case you might want to have a way to customize it. Or a multiplier. Say you have a multiplier module and you want to be able to customize the size of the inputs and the outputs of the multiplier, right? You could build a 16-bit multiplier or a 32-bit multiplier. That's the way you do it. Now the syntax here I think is very strange, and I can almost never remember. This is another one I can never remember. I always have to go back and look it up. So the syntax is that the parameters are defined on the module line, right, which makes sense. But the way you do it is you have module and then the name of the module, in this case adder, and then you list the parameters, but you put them in parentheses and you put a hash sign or a number sign there first, okay? And then you have parameter, name, default value, comma, and as many as you want. And then close that parenthesis and open up a new parenthesis for the inputs and outputs. Make sense? And then you can use those parameters inside the adder, which I don't actually do here, which is, I do, not inside the adder, I do actually here in the IO list though. So A is in with -1 down to 0, B is in with -1 down to 0, and S is out with -1 down to 0. So for example, if in with were 8, that would be an 8-bit inputs, so it would be 7 down to 0, that would be translated into 7 down to 0, 7 down to 0, and then my out with might be, say, 9, in which case that would translate into 8 down to 0. Does it make sense? So you can use the parameters in the IO list, and you can use them inside the module definition. Does that make sense? Okay, now you might say, well, what's so confusing about that? Well, here's the problem, is that when you use the module now, you'll say adder, then your hash sign, and then open parenthesis, and then you set your parameters using the same kind of format you do with the pins, where you say dot in with 10, dot out with 11. Obviously, these have to be assigned as constants, because these are being baked into the hardware when you instance this. Okay, and then my adder, and then your port map, right? Now this is why it confuses me, because if you look up here, you've got module, adder, then your parameters, and then immediately following the parameters, you have your pins, right? But when you use it, it's the name, the module name, then the parameters, then the name of the module, then the pin map. So notice that the name of the module comes between setting the parameters and setting the inputs and output ports. That name, that name comes in between there. But when you declare it, there's nothing in between there, right? So that's why, to me, maybe not to you, but to me that was always confusing because I could never remember where to put the parameters when you, because oftentimes, like I'll take the parameters and I'll put it before, like I'll put it between module and the name of the module, and of course that generates the syntax here. But it's one of those things that you might have to go back and check before you use it. Does that make sense? Okay. All right. Okay, and this is the last syntactic thing for system Verilog is that we're going to cover is the generate statement. So I talked about this in lab. You guys might already know this now. I'm just going to go over it so I have it in lecture. The generate statement allows you to essentially take a block of code and really just kind of copy and paste it, but not have you copy and paste it. You have the compiler copy and paste it. So it's used for creating an array structures. Like for example, if you want an array of adders or an array of functional units or an array of cores, but you just want to write one piece of code and have it replicated when the compiler compiles it, right? So the way that you do it is through this generate for loop. Now there's two kinds of for loops in Verilog. There's a generate for loop, and then there's another for loop that you can use inside of an always statement. I don't think I've ever used, actually I have used the for loop inside the module the always statement, but only for test benches. That's non-synthesizable code. In terms of synthesizable code, I don't think I've ever used an always for loop, but I have used a generate for loop. So I know it's kind of, what's the difference? Well, the difference is that notice that this generate for is outside of an always block. But there's kind of a strange syntax here. So you have gen var I, which is the variable you use for the for loop. And then generate for I equals 0, I less than n. Now n has to be a constant, and so in this case it's a parameter, but I could, of course you could just type it in the constant there. And then I equals I plus 1, I plus plus does not work here, right? Then you have begin, that makes sense, but then you get colon and the name of the generate statement. I don't know why they require that, and that's hard to remember. That's the syntax they force on this. And then you have, at the end, you have end and then generate. Okay, so then anything between the generate and the end and generate is going to be, in this case, it's going to be replicated n times. Now, the cool thing about this is this stuff in here can include assigns, it can include module, like structure, like I have here, or it can include always blocks. You can put whatever you want. Any Verilog can be in between this, and it will just get, and it can be multiple statements too. Like you could mix and match. You can have some modules in there, and you can have some assign statements in there. But whatever you have in there, it'll get replicated, right? Now in this case, the only thing I have in here is I'm instancing this adder. So I'm creating n adders. Now the thing that differentiates one adder from the next is basically just the bits, the way that I do the bit arithmetic here. So you've got this I, and the I is intended to be used for indexing operations for bits. Now, can you use it for anything else? I don't know. Maybe? I don't know. The only thing I've ever used the genvar for is for bit indexing. So what I'm doing here is I'm building a big adder from smaller adders by concatenating them together, right? Actually, not a big adder. I'm creating a SIMD adder, a vector adder, because I'm not passing a carry from one adder to the next, so it's not actually building a bigger adder from smaller adders. In order to do that, I would have to deal with the carry. I'd have to have carries going from lower adders to bigger adders, which I don't have. So this is what this is doing is creating an array of adders that adds two vectors together, right? In which you've broken the carry chain between the adders. You guys with me? Does that make sense? Like, so if I add two vectors, when you do vector addition, you know, the elements of the vectors are added individually, you know, so there's no carry between the elements, right? Okay, so basically this is creating an array of n adders, and so for each one of those adders, I set parameters in with and out with. Obviously, this is the adder from the previous slide. Do these matter for the generate? No, the parameters don't have any effect on the generate. They're all hard-coded to be 8-bit adders. Okay, I just put that in there so I could have a running example. Then I create my adder. Right, now remember the syntax here is strange. Adder is the module name, then the parameters, then the name of the module, then the port map. Now the port map is where the interesting stuff happens. So the A input on each adder is connected to big A. Big A is, in this case, these are 8-bit adders, and big A is 32 bits. And N is 4. So this is going to create 4 adders that are 8 bits each that add a vector that's 32 total bits. Now, you might say, well, that's kind of bizarre. Why would you do that? This is actually very common. Intel processors have these instructions called, well, they started out as SSE instructions, or no, they started out as MMX instructions. Then they became SSE, and then they keep changing the name. But basically, these are the vector multimedia type of instructions which are used in this case. Like, why would you add 4 8-bit values? Well, that represents a pixel. That's red, green, blue, and alpha, right? So this is like adding pixels, which have 4 color planes, right? So that's what's happening here. And then, but the thing is that big A is the pixel value, which is a packed 32-bit value containing these 4 independent values. And then I'm generating 4 adders, 4 independent adders. And so when I connect the A input, I have to do a little math here to figure out for each one of these adders which ranges of bits do I want to send in. Well, the math is 8 times I plus 7 down to 8 times I. So when I is 0, this is going to be 7 down to 0. When I is 1, this is going to be 15 down to 8. When I is 2, this will be 23 down to 16. And when I is, sorry, I think I got ahead of myself there. When it's 0, it's going to be 7 down to 0. When it's 1, it's going to be 15 down to 8. When it's 2, it's going to be 23 down to 16. And when it's 3, it's going to be 31 down to 24, right? So basically, it's going to take a different slice. It's going to divide up big A into 4 slices. And then because I'm doing some arithmetic dependent on I can slice out which bit range I want, right? Now you might say, well, how does this relate to anything we're doing? Well, in the next lab, we want to be able to independently control a pulse width modulation of all 26 LEDs on the board, independently, right? So we want to be able to have all 26 LEDs at different brightnesses, right? So what you're going to want to do in the next lab is you're going to want to create a 26 times 24-bit, however many bits you want to represent your duty cycle. So each of the 26 LEDs has a bit duty cycle, right? So you're just going to put all those duty cycles into one long bit string declared like this, and then you can have now you don't have to do this, by the way. You could copy and paste 26 chunks of code for each LED. You're welcome to do that if you're more comfortable. But if you choose, you can use a generate statement, which makes this much easier. So you basically will have all the code required to drive the LEDs with a pulse width modulated signal, and you just have that inside this generate that goes 26 times. Generates 26 copies, and then each one of those copies will have a separate duty cycle and keep track of the duty cycle. Because remember, you start out at 100% duty cycle and then it fades, right? So that way you say, you tell it which LEDs you want to turn on, and then after you turn them on, within 1.3 seconds, they fade to zero. They fade to black. Does it make sense? So that's why this is relevant for the next lab. Like I said, you probably want to use a generate for that. Because remember in the last lab, we did the same thing. We had piecewise pulse width modulation, but you had all the LEDs were like synchronized, right? We want to desynchronize them now and have, control them independently. Okay, and then I talked about this in lab, but yeah, actually I'll just skip that for now. Okay, and then another thing we talked about in lab, but I want to get it on the record here in lecture, is how to set up probes and sources. So this allows you to, obviously the probes and sources use parameters, which is why I talked about those here. So you just say alt source probe. This alt source probe would normally be a module, but in this case we don't have a module called alt source probe. So what is it doing? This is a primitive. This is actually a special word that the compiler recognizes as something that you want to access physically on the chip. And so this allows you to set the widths of the probes, and you can give it a name, and then connect sources and probes. The source is something you can set, and the probes are something you can monitor, right? Does that make sense? In the sources and probes editor. And then the other option is signal tap, which, yeah, I'm going to go through and I'm going to actually do a quick demo of that now. Let's see if I try to see it. Angela will bring a board down, but no, okay. All right, no problem. Okay, so let me go ahead and fire up Quartus. Okay, I'm going to just open up a lights project, which is one of the examples with the SOPC, or the platform design system. Come on. Let's see if I could set the virtual screen here to there we go, that's a little better. Okay, all right, so if we open up lights, this is the top level design. This is the one from lab 2. So I've got my top level inputs and outputs, and then I have the Neo system here, which is, basically all this is doing is reconciling the naming difference between the names that Platform Designer uses and the names for the actual pins on the chip. Does that make sense? So it's just a one-to-one mapping. So this is nothing but a wrapper around the Neo system. If I go here to Files, double-click on neosystem.qsys, I can check that out. I can open that up. Okay, so in this lab, we want to create an IP block inside Platform Designer. So this will allow us to add our own hardware into the Neo system as a peripheral, in this case, as a slave device to the Neos processor. So this will allow us to write and read data between the software and the hardware that we're going to design. So in this case, I'm going to take this LEDs. I don't know if you could read that in the back, but that's a parallel I/O. This is how we were setting the LED values. I'm going to delete that because I'm going to create my own module in here that will control the LEDs. So to do that, you just double-click on New Component here, and I'm going to call it LED Blinker. That's the name and the display name. And then I'll go over here to Signals and Interfaces. And so this is pretty easy to set up, actually. It's just a little, the user interface is a little wonky, but You're going to need a clock input, so I'm going to add a clock input. I'm going to add a reset input, because pretty much everything's going to have a clock and a reset. And then I'm going to add a Avalon memory mapped slave. That's going to allow the processor to send and receive data from this thing using programmed I/O, using the Avalon on-chip bus. And then I'm going to add a conduit, which allows me to actually go out to the LEDs. So these are the 4 things I need: slave interface, clock, reset, and a conduit. The problem is that I'm not done. I have to go under each of these and add specific signals. So for the Avalon slave, I need an address. Actually, I don't need an address. I need a write. That's the write signal, tells it when I want to write, and I need a write data. And that's it. So in the lab sheet, I actually told you to add an address there too, but you actually don't need that. That's optional, because you would need an address if there's multiple addresses that we want to write, like multiple different word types of data we want to write. But in this case, there's only one thing. I'm just telling it which LEDs to light up, right? So I don't really care about an address. The reason I said to add an address in the lab sheet is because I thought you had to have an address, but it turns out I found out later that you don't. But it's up to you. So I just have write and write data. And then for the clock sync, I need to add an actual signal called clock. For the reset, I need an actual signal called reset. And for the conduit, I'm just going to add a star signal. And then I have to update some of the parameters here. So for write, that's a 1-bit. The write data is 32 bits. You might say, you only need 26, but I'll just use 32. For this clock, I'm going to rename these clocks so the naming is a little bit more manageable here. CLK for that, and I'll call this CLK. Likewise, for the reset, I'm going to rename that RST, and for the internal signal here, RST. And then for the conduit, I'm going to call that LEDs. And signal type is going to be, I don't know what that's all about. I'm just going to say star. And the width is 26 bits, and it's an output. Why is it doing new signal? I don't want new signal. Star. Thank you. And then for the Avalon, if you jump back up to that, you have to specify the reset. And that's it. That's all you need. So that's ready to go. And so I'm just going to hit next. And then if you hit next, it just goes to these tabs. Now the problem here is that the final step is to create a synthesis file, to create like a wrapper, like a template file for this. So you click that, but the problem is it wants to call it newComponent.v. I don't want to call it newComponent.v, but the only way I've found to get around this is if you hit finish on this and hit save, and then go back to the LED blinker, do a right click and say edit, which brings me back to where I was, and then I go to files and hit create synthesis file, and now it allows me to call it LED blinker.v. That's what I want to call it. I don't know why you have to do that. That's just a now notice the HDL language is Verilog or VHDL. I'm going to pick Verilog, hit save, and then finish, and say save, and then save everything here. And then now that I have that IP block, I can add it into my system as soon as it finishes running these scripts. Come on, buddy. Okay, then I can add it. Double click on the blinker. There's no options because I didn't specify any, and then all I have to do is connect the slave to data master on the processor, conduit, or actually the clock. I'm going to do system clock, sysclock. Reset's going to be the same reset everyone else uses, and for the conduit, I'm just going to add a conduit called export that is called LEDs. All right, done. Generate HDL, generate. That's all you need to do to create a block. Now, when you go back to Quartus, you can do file open, and you'll notice that the LED blinker.v is now available inside the project. So I'll double click that, and now I can put my implementation in. My implementation is going to go inside this module, and as I mentioned, these are declared as wires, right? But I've got an Avalon slave write, which is just a single bit, tells me when I write. Avalon slave write data is the data it's writing. LEDs is my output, my only output, and clock and reset. So I have 4 inputs and 1 output. Okay? So let's say now I want to monitor these guys to see what's going on, because the Avalon bus, I didn't really cover that in class specifically. We talked about SPI and I2C. I didn't really talk about Avalon. So how do you know how the Avalon bus works? Well, there's a timing diagram inside the wizard for that. So if you go to Platform Designer, and I edit that guy. Oh, hold on, close, sorry. Okay, edit, do right click and say edit, and then you go into signals interface. If you click on that Avalon slave, it'll actually show you the timing diagram down here. And you can see it's pretty simple. It basically, whenever the processor wants to write, in other words, when your software, you're going to write C code, which is going to write using the IOWR intrinsic, that's going to raise the write signal for 1 cycle, and then you're going to get the corresponding data, right? So it's just basically, it's like having an enable for a register, using the, so you're going to use the always statements that had the enable. So when I go back to Quartus, I edit this file. First of all, I can monitor what's going on there with signal tap, but the problem is I'm going to need a, I'll show you how to do that. I have to run this through the compilation first to do that. But before I do that, let me go ahead and just add an always at pause edge clock begin end. Okay, so I can say I can have a logic 31 down to 0 called count limit, and then I can say on the rising edge of the clock, if Avalon slave write is asserted, then I can set count limit to be Avalon slave write data. So this will allow me to implement a control register So if I have a write signal from the processor, then I'll capture the data that I'm writing from the processor. So in other words, what I'm saying is that Avalon slave write data is actually the value that you would put in the IOWR call inside your C code. You guys with me? So that's the stuff in your software that there's a value now. This is a way that you're taking a variable in your software and you're doing a write, which is writing that value across the Avalon bus, which will then come into the system Verilog design and will become this Avalon slave write data. Now you might say, well, wait a second, what about the address? Where's the address go? Well, we don't have an address because what will happen is this whole thing gets assigned an address in, oh yeah, close this. Don't save. So I have an address now. The blinker, the LED blinker, has an address of 0 to 3. Remember, this is a byte address, right? So the byte address is in bytes, and the data is 4 bytes, 32 bits. So the address that maps to that peripheral spans addresses 0 to 3, which is it's 4 bytes, right? So in the software, if I store to address 0, that will be interpreted by the Avalon system as something you're targeting to the blinker. So in the blinker side, the blinker will then see that write signal go high because the address the software used targeted that peripheral. And you might say, well, who does that? Where is that implemented? Well, that's just part of the Avalon. That's a decoder that's inside the Avalon bus. You don't have to worry about that. That's something generated by Platform Designer, right? So when you write to address 0 in your C code, that's going to get translated to, that's a way that the software is going to pass a value to the hardware. You guys with me? And because there's only one word there, there's no point to have an address because there's only one addressable location in there. So that's how I get away with not having an address. If you put an address in there, like I said to do in the lab sheet, and you make it 1 bit, then it'll end up being 0 to 7 because you'll have 2 words you can address. But then you can still choose to ignore the address value inside the module, in which case you effectively have 1 value. Does that make sense? Okay, so now now I've got hardware that will allow me to capture data that the software sends it, and that's pretty much all it does for now. Let me, just to make sure this doesn't get optimized out, I'm going to assign LEDs to be Avalon slave, right? Sorry, no, not that. Count limit, rather. Count limit. Okay, I'm going to assign that because, and I got to be 25 done to 0. Yeah, I have to assign that, otherwise it would optimize this out because there's no actual output from this guy. Okay, so I'm going to compile it, and then we'll add some probes to actually watch the transaction happen. Hopefully it doesn't take too long because I've only got 2 minutes. Any questions about that? So setting up the IP is like trivial. I did it, you saw I did it in just like a minute. The tricky part though is putting your logic in there and then writing software that then works with the hardware. I don't know if I generated that. I might not have generated I might have forgot to hit generate HDL here. Yeah, I bet I did. So it's the Quartus is not seeing that new module. Okay. Well, I'll tell you what. I'll finish this demo up. I'll finish it in lab, and then I will give you a copy of this that you can use, like as an example. There's more to it, though. I had planned to put to make it so you could write a value in that tells it how fast to blink the LEDs was my plan, and then I was going to show you how to monitor that with SignalTap, but I ran out of time. But I'll show you that in lab, and then, like I said, I'll give that out as an example. Any questions? Okay, great. Well, then I will see you. Wait, am I out of time? No, I actually have 10 minutes. No, I'm good. Sorry, it's 25, not 35. So let me let this finish, and I will show you how to add the SignalTap. We'll have enough time for that. Go back to Quartus and compile. Now you might say, why are you compiling now? So I talked about this in lab, but SignalTap allows you to add probes to signals in a deployed design, but you have to compile it before you do that. So in other words, you have to compile twice. You have to compile it just to make the signals visible to SignalTap, and then you add the probes, and then you have to compile again, because every time you add signals in SignalTap, you have to recompile. Now that's pretty awful. I hate that, but I don't know of another way to do it. I haven't found a better way to do it. But anyway, once you get that compiled, you go over here to Tools, SignalTap, Logic Analyzer. And you just have to set up your clock. So you hit ... there. You change this type to pre-synthesis and hit list. Actually, it's a filter. The filter is, that's registers. Man, I screwed that up. Sorry. SignalTap pre-synthesis. There we go. Hit list. Now this should show clock. It's not going to show the new stuff yet because it's still compiling, but I should get clock. Come on, SignalTap. Quartus. Okay, here we go. So I had it list everything that's available in pre-synthesis, and you can see that at the top level under lights, I have, remember lights is the top level module, I've got all my pins, or at least the pins that I'm using. So clock 50 and the DRAM pins. And then I've got the Neo system, which I can then drill down under. So if I drill down into Neo system, I should be able to see all the things that are available into there. And so I've got some stuff in there, but pretty much just the DRAM stuff, because everything else is optimized out. Okay, so I'm going to take clock 50. I'm going to hit the button to bring that over, and then add that. And there it puts clock in here as the clock. That's the capture. Now you might say, why do you need that? That's the rate at which I'm sampling. So the way it works is you have a trigger, and after that trigger occurs, it will start capturing values until it fills up the buffer. The buffer in this case is 128 samples, which you can make that larger if you want. You can say 1K for instance. The other thing I just realized too is, I've got an error and I know what that error is. So the problem is that I forgot to update the Neo system. So remember I had the Neo system here, this is the original one, and I had a thing called LEDs export. That was from the Parallel I/O. But now I'm going to use my custom IP block to drive that. And so I don't even know what it named that. So if I go to open Neo system, I can open neosystem.inst.v, and notice it names it LEDs new signal. That's why I kept trying to get rid of that new signal thing in there, but that's fine. So actually I just need the new name. So I'm going to go back over to lights.sv and just replace LEDs export with LEDs new signal. It's going to be connected to the same thing, which is the red and green LEDs. So I'll save that and rerun that. Let's see, anything else? Oh, and the other thing is, okay. The other problem is under the LED blinker.v, I also made a mistake there by declaring this CNT count limit to be logic. Remember, this is Verilog, there is no logic, so I have to make it a reg. And likewise, and that's it. I was about to say the LEDs, this LEDs, because I'm driving it in here, do I have to rename that as a reg? I don't, because that's an assign, right? So if I have an assign, if I use assign to assign LEDs, I can leave that as a wire. But this count limit has got to be a reg because it's set here inside of an always block, right? So that's just, because this is a pure Verilog file. Now you might say, wait a second, that's Verilog, but lights.sv is system Verilog, and they're being compiled into the same FPGA. Is that cool? Yeah, it's fine. It's just for whatever reason, the IP blocks have to be Verilog. There's probably a workaround to that. I just haven't found it yet. But basically, LED blinker has to be Verilog because it's an IP block, and lights.sv is system Verilog because I just chose to make it a system Verilog. All right, let me rerun that. Okay, now notice this time it says stp1.stp has been modified. Do you want to save your changes? That's the signal tap file. You want to save that signal tap file. Yes. So signal tap, it gets listed under the files for the project. Right there. You see that? It put it in Neo system. I prefer not put it in there. I'd prefer to put it in the main project directory, but that's fine. So under the Neo system, I've got stp1.stp. The reason I put that in there was because that was the last directory I opened a file in. Okay, but now we're good, right? It's going. It's compiling. And once that compiles, I should be able to go into signal tap. And what I want to do is I want to probe those Avalon signals. So that would allow you to, not only the Avalon signals, but any internal signals inside the module, like that count limit. So then you can actually watch, when the software writes to that address, you can watch it. You can see the transaction in the logic analyzer. Okay. Now the reason this is slow is because I'm running this on a virtual machine. It's not going to be this slow in the lab. Any questions so far? Did I lose all of you with this? So the reason I'm emphasizing signal tap is because this is the main tool for debugging your design. I mean, you know, if you design this stuff and you put it on the board and it doesn't work, you know, like what do you do? What do you look at? Well, you have two options. You have the debugger for the software, so you can walk through each line of code with the debugger and see what's going on in there. And then for the hardware, you have signal tap and the sources and probes. Signal tap is usually more useful than sources and probes because it has that ability to trigger. You can set a trigger. So in this case, I would want to trigger on when that write signal goes high. That Avalon write, which is this signal, Avalon slave write, I would trigger on the rising edge of that signal, which would allow it to capture when the write actually takes place. So, because you know, you run the software, but you don't know, you need to nail down exactly when the software initiates the write to this peripheral. And so if you trigger on the rising edge of that, you can capture that moment in time and look at it in the waveform, the logic analyzer. You guys with me? By the way, when I say logic, if you haven't heard that term, a logic analyzer is a bench instrument that you usually have, like it's a big box that you have on your bench, and you usually has a ribbon cable on it that you bring down and you connect to pins, right, on your board. And then you can watch, and we actually have them, we have a small logic analyzer built into the oscilloscopes that are in our lab that have 16 bits, I think, you can measure. So there's a little ribbon cable that comes down, and it plugs in, and you can watch like a waveform of digital. Now that's the difference between a logic analyzer and an oscilloscope, is that logic analyzer is digital and oscilloscope is analog. Right? So an oscilloscope shows you an analog value, whereas a logic analyzer shows you a digital value, and usually multiple parallel digital values. So, you know, you see, like I said, in this, I think we've got 16 or 32 bits you can hook up with the scopes that we have in the lab. But in this case, signal tap is a virtual logic analyzer. You don't have to use the box, the physical box. You're doing it over JTAG and monitoring in Quartus and signal tap. So it's kind of like a logic analyzer, except it's not a physical logic analyzer. It's a virtual one operating over JTAG. Does that make sense? You guys with me? This way you don't have to hook up little tiny wires. You know, that's frustrating. I hate doing that. This way it's all kind of, you just set it up in signal tap and you get it. Boy, this is taking forever this time. Okay, well then I will, like I said, I'll finish this up in the two labs, and I'll give you this example, and that way you'll see how to set up the component and test it. Okay, thank you.